Okay, so today we're talking about solubility rules. So solubility rules are a way of making predictions of whether combinations of ions are going to solidify. Okay, on your lab, the last lab, the conductivity lab, there was the last question that said, what would happen if you had one solution and then you added another solution, and as you added the second solution, the conductivity started to go down? Okay, so there was actually two acceptable answers for that. One of which being your second solution could have been less concentrated than the first. Okay, so that's valid. And then the other one being that your ions would start to clump together to form solids. And if they form solids, they're no longer conductive, right? Because remember, in order to conduct, they got to be able to move, right? Okay, so the solubility rules group ions together so that we can make predictions. So there's 6 rules here, and these look complicated at first. You don't have to memorize them. I will give you this very same exact list, okay, but you have to be able to interpret it correctly. So let's start with the first rule. Oh, by the way, solubility rules are based on whether you have 0.1 molar concentrations, okay? If you have concentrations other than 0.1 molar, then this list is not valid. Okay, so only applies to this concentration. 0.1 molar is a standard lab concentration, like anywhere you go, so that's kind of why we came up with this set of rules for this. All right, first rule, all nitrates. When we say all nitrates, what we really mean is any compound that contains nitrate. Okay, so for example, this is sodium nitrate. Just for short, we lump it into a category called nitrates. It's a compound that contains nitrate. Here's another one. This one is called copper 2 nitrate. Any compound that contains nitrate is a soluble compound. That means it will dissolve. The ions will separate. So let's kind of just reiterate that. Will dissociate, which is a fancy way of saying ions separate. The second part of this rule is for acetates. Now, acetate is a polyatomic ion, and any compound that contains it is called an acetate. So here's an example. KC2H3O2, that is called potassium acetate. That is a soluble compound. I know that I can dissolve potassium acetate in water, and the ions will split up and dissolve. Okay. The second rule pertains to alkali metal ions, lithium, sodium, potassium, rubidium. We could also include cesium in there and francium if we wanted to, but those are so rare that they're not commonly seen. So, all alkali metal ions is the bottom line, okay? Any compound that contains an alkali metal ion is completely soluble, and the ions will separate, right? So, I pick any one of these, Na, and then pick any polyatomic ion from anywhere. Na2SO4, for example, that's called sodium sulfate. That's a completely soluble compound. Those ions will separate, and you will not see any solids forming. By the way, let's bring up this word. I kind of realized I just glossed over it. The word precipitate is when solids form. So anytime we mix two solutions and we see chunks form, that's called a precipitate. You have done a lab where you saw this. It was our double replacement balancing lab. You had a little glass well plate. You had a bunch of different solutions, and you were writing down whether they're chunky or whether they looked like there was a color change, whether there was fizzing, right? So those were precipitates that you saw when you saw solids form. Okay, rule 1 also includes ammonium, NH4 positive. So if NH4 positive is in a compound, that is a soluble compound. You can even have something like this, NH4 There's 3 ammoniums in that compound, but that's a completely soluble compound. Okay. Rule 3 applies to what we call the halides. Halide is what we call a halogen that is charged. Remember the halogens, fluorine, chlorine, bromine, iodine, right? But if it's an ion form, we change it. We don't call it a halogen anymore because halogen means Cl2, Br2, I2, F2. Okay. Halide means it's charged, and so it's Cl minus, Br minus, I minus. All right, so the charge. Okay. So halides, except for when they're with silver, lead, or mercury, are soluble. So this is our first complicated rule. Anything that has Cl minus, Br minus, or I minus in it is going to be soluble, except with these 3 exceptions. Okay, so zinc chloride is aqueous. Remember, aqueous means dissolved. It's soluble, it's dissolved. But lead chloride is not. And so because it is not soluble, it ends up precipitating into solid chunks, and that's why we use the S symbol here. Right? S means, when you see S, that means solids form, which means it's insoluble. And that can be kind of confusing because you almost think that S would mean soluble, but it doesn't. S means solid. AQ means soluble. All right. Since we're here, I'll give you another example of that. Iron 3 bromide. It's a bromide. It's not the metal is not one of the exceptions, so therefore this is aqueous. It is soluble. But AgBr is not soluble. It will form solids, and that's why we write an S. Is this making sense how this works? Okay. Again, don't burden yourself with thinking that you have to memorize these. You just have to be able to read these correctly, all right, and apply them. All right, rule 4 is also kind of, complicated. Most sulfates, so sulfate is when you have SO4 minus 2, okay? SO4 minus 2, that's sulfate. Most sulfates are soluble, except those bonded to calcium, strontium, calcium, strontium, barium, mercury, silver, and lead. So there's 6 exceptions. So if I wrote MgSO4, what would MgSO4 be? Would it be aqueous or would it be solid? It would be aqueous because it is soluble. Most of the sulfates are. But if I wrote SrSO4, strontium sulfate, that is one of the exceptions that is not soluble. It will form solids. It will precipitate out, and you'll see cloudy chunks. Okay, so rule 5. Hydroxides. The polyatomic ion hydroxide is OH minus. Now here is where we flip the rules. Notice up until now, rules 1, 2, 3, 4, we were assuming that most things were soluble. Now we're going to flip it, and it's just easier to say that all hydroxides are insoluble, except for, and now the exceptions you list are the ones that are soluble. So hydroxides are insoluble, except if they are with alkaline metals, barium, or strontium. Okay, so NaOH. What do we put there in the parentheses? So the thing about Na is an alkali, right? Alkali metals, guys, remember first group? Lithium, sodium, potassium, rubidium, cesium. Okay, those guys are soluble with everything, right? That was actually a rule. What rule was that? Alkali metals are soluble. Rule 2. Okay, so sodium hydroxide is aqueous, but zinc hydroxide would form solids. You're going to become really familiar with these polyatomic ions after a couple worksheets of working with this. I mean, I know you know some of them already, but you're just going to be looking at them a lot. All right, and the last rule. The last rule is a catch-all, sort of. All right, we've got phosphate, carbonate, and sulfates all smushed into one rule. And the reason why we put them in the same rule is because they all behave the same way. These polyatomic ions, when they are in compounds, they are all insoluble, except for alkali metals and ammonium. And in case you forgot what ammonium was NH4 with a positive charge. So, something like PbCO3. That's a carbonate. So what should we put in there? AQ or S? Yeah, S. That's insoluble. Sulfide. So sulfide is S with a charge of -2. What if you saw something like this? K2S. Is that compound aqueous or is it solid? That one is aqueous because the cation is an alkali metal, and those are always soluble. You will not have conflicts between rules 2 and any of the others. They won't conflict, right? So that's kind of nice, right? There's not like, but you still have to interpret the rules and the exceptions correctly. All right, so how is this applied? We have this list of rules, so what? You look at a compound just to tell if something is a precipitate or not. Well, the application is we mix things all the time, right? We mix things all the time in the lab here, but even commercially, right? If you're a pharmacist, right, and you need to come up with something that will dissolve once it's, swallowed from pill form, right? Or if someone's on multiple medications, they got to make sure that when the patient takes more than one medication, that those two things don't clump up, right? Because otherwise it would be ineffective, right? They have to make sure they're soluble. So these rules are really, really, really important in like healthcare and pharmacy, right? Also in water systems, right? And for like civil engineering. Okay, so how does a problem like this work? What do we do? Here's how they generally look. All right, so they tell you we mix a solution of barium nitrate with sodium carbonate. Okay, so the first thing you need to do is write the formulas. Barium nitrate has a +2 charge, sodium is -1, or nitrate has -1, sodium is a +1, carbonate is -2. Check your charges, write your formulas correctly. Then split everything up. Split up all of your ions, right? Write them separately. So the barium is written by itself, the nitrate is written by itself, the sodium is written by itself, carbonate is written by itself. Now, the thing that you should remember about these types of reactions is we have a classification for this. It's called double replacement. Okay, so the sodium and the nitrate will end up together, and the barium and the carbonate will end up together. So we're going to rewrite them to reflect that. And of course, pay attention to the charges. Make sure that you know +2, -2, +1, -1. Once you have predicted your formulas for your products, check your rules, right? And so if we go through this and say, all right, NaNO3, is NaNO3 aqueous or is it a solid? So you check your rules, and so but rule 1 says all nitrates are soluble. Rule 2 says all sodiums, all alkalis are soluble. So this is soluble according to both rules. All it would need is one rule, by the way. It doesn't need both, right? So it's perfectly soluble. The barium carbonate is insoluble because carbonate is mentioned in Rule 6. So, we figured out what is insoluble. We figured out what the solid is. So what we do is we write a reaction. This is called an ionic reaction because it is showing ions as reactants. Okay, notice how everything here is separated into its ion. On the reactant side, you write all your separate ions. On the product side, your solid is written together as one formula. But your ions that were soluble, we still stay separate. And there's a reason for this. We want to algebraically simplify this equation, which means any redundancies on the left side and right side will cancel out. 2 nitrates, 2 nitrates, 2 sodiums, 2 sodiums. And once they're canceled out, you are left with the simplest form of this equation, which is called the net ionic equation. The ions that did not solidify are basically ignored. They are left out. The only ions that you used are the ones that ended up in the solid. Okay, that's our end goal here, to be able to do that. So let's follow the same set of steps, see if we can come up with a couple of these. All right, we're going to mix barium chloride and sodium hydroxide. The first thing you need to do is realize what the formulas are. Okay, so you need to look up charges. So barium is a +2, chlorine is -1, sodium is a +1, hydroxide is OH with a -1. Okay, so because this is double replacement, you're going to have to pair what with what. Give me an example of a pairing here for our products. Okay, the barium and hydroxide will end up together. And then, of course, by default, sodium and chloride. Now, if barium and hydroxide end up together, you need to check your rules. Is there a rule about barium or hydroxide? I'd say Rule 5. Rule 5 says hydroxides are all insoluble except with barium, which means it's no longer insoluble, which means it's no longer insoluble, which means it's soluble. Okay, so that means BaOH2 will be aqueous. I'm going to pause right there and make sure that makes sense. Is everybody following what just happened? We looked up the rule for hydroxide. Hydroxides are all insoluble except for a select few, except for alkali metals and barium and strontium. And barium is one of those examples. So therefore, this is not insoluble. Okay, sodium chloride. Is there a rule about sodium or chloride? Rules 1 and 3. Or not 1, 2. Rules 2 and 3. So alkali metal ions, right here, alkali metal ions are soluble. And Rule 3 says that chlorides are soluble except with silver, lead, and mercury. Well, I'm not worried about those right now. So NaCl is definitely soluble. Okay. If both of your products are soluble, that means you don't actually form a solid, and then there's no reaction. Nothing happens. I can mix these two, and you will not see anything happen. And that happened a couple of times in that lab, right? Every now and then you'd see one where you mix drops together and nothing happens. It's so totally okay. It can happen. Okay, let's try the next one. So lead and iodide will come together. Potassium and nitrate will come together. So we need to check our rules. Lead, that's a charge of +2. Iodide is -1, so therefore that's the formula. Potassium is a +1. Nitrate is a -1, so that formula is okay. But we have to check the rules. So PbI2. Can someone tell me what they think that's going to be. Is that going to be aqueous or is it going to be solid, and which rule says so? Nick?
PbI2 should be soluble.
Well, what rule are you looking at?
Never mind. It should be insoluble because of rule 3.
Okay, so iodine, it's right here. It's a halide. All right, iodines, they're soluble except for these three. And so this is actually the one we're working with right now. So this is an exception to the rule, which says it is not soluble, right? So it will be marked as solid. Okay? Now, just because we found one of them doesn't mean we don't look up the other. We still look up the other because your reaction can have one solid or two or none. So KNO3, is there a rule that tells us what KNO3 will be? Rule 1, all nitrates are soluble. So that one is AQ. All right. We have identified the solid. We only use ions that lead up to the solid. So our net ionic equation will be Pb plus 2 plus 2 of the iodide ions that form the solid PbI2. Oh, forgot the AQs on these guys. Okay, I want you guys to try the third one on your own.
What if the original compound is not soluble?
It can't happen. You won't be given one.
Okay.
Because it has to start as a solution.
Right. It has to break apart so that it forms precipitate.
So, what's our solid, if any?
AgCl.
Yeah, AgCl, right. So, your products would have been KNO3 and AgCl, but again, according to Rule 1, all nitrates are soluble, and Rule 2, which all alkali metals are soluble, so that compound is aqueous. AgCl, it's a halide, and halides are soluble except for silver, lead, mercury, so that is our solid. So our net ionic equation will contain just those ions. And your product is the solid. How we doing? Good? Awesome. All right. That's all